Chapter 6, Alkyl Halides. In this chapter, we will learn how to name alkyl halides. We will look at reactions alkyl halides can be actually made through, or reactions that alkyl halides can undergo. In this chapter, we're going to focus on the main type reaction that alkyl halide undergo, that is nucleophilic substitution. So alkyl halides, usually when we look at the structure of alkyl halide, they can be part of a certain category of those alkyl halides. They can be an alkyl halide, where basically there's a methyl or an ethyl or a propyl or whatever that carbon that's going to be attached to, or it could be a vinyl halide where you have an S2 carbon attached to it, so you're going to have basically an alkenyl halide, or it could be an aryl halide where you will have a phenyl group attached to that halide, and the halide can be basically a fluoride, bromide, iodide, or a chloride. Every single CX bond, it's always going to have some polarity in it, and the polarity will always depend on the electronegativity value difference between the two, the carbon and the halide. And in all of these alkyl halides, alkyl halides or vinyl halides or aryl halides, you will always see the electron density lies toward the halide, the fact that it's more electronegative. And that makes the carbon that's attached to the halide more electropositive. And this partial positivity of on the carbon, it allows it to basically be nucleophilically attacked. What is that supposed to mean? That means those alkyl halides, we're going to see them reacting as electrophiles due to the electrophilicity of the carbon attached to the halide. And that's where basically the nucleophile is going to come in and attack, and that will allow the halide to leave. So those nucleophilic substitution reactions that we're going to look at later on today, we will always see in there that a nucleophile comes in and attack the alkyl halide on the carbon side of the CX. And since the carbon cannot accommodate more than 8 electrons shared, therefore the halide will be the one that's leaving, taking along with it the 2 electrons that are bonded between the carbon and chloride or the halide. And in terms of nomenclature, they will follow similar rules to what we have learned already in the alkane chapter, which is basically going through a set of steps. The first step would be finding the longest chain of carbons. Second step would be numbering the carbon chain from the side that's closest to the nearest substituent. And you always want to aim for the lowest numbering possible for the substituents. So let's look at some examples here. Here's the first example. We see that we have the longest chain of carbons is 4, and we number from the left to right, not from right to left, as it is closer to the nearest substituent. That will be the carbon number 2, where the chloro is. So the name would be 2-chlorobutane. It could be a complex substituent sitting on a longest chain of carbons. In that case, I don't number the chain where the halide is. I number the chain that's going to give me the longest chain of carbons, because halides are not function groups. They are substituents. So keep that in mind. Do not number the chain that has the halide if there is a longer chain of carbons that can exist in the molecule. And here's an example. We can see here that we have 7 carbon chain. If I go through the carbon where the fluoro is, I'm going to have 6 carbons instead of 7. If I do it the other way, I'm going to also have 6 carbons instead of 7. So therefore, the fluoro becomes part of the substituent that's sitting with the longest chain of carbons. So what is that what is that substituent? That substituent, since it's more than 1 carbon, will be numbered from the first carbon immediately attached to the longest chain. That will be number 1, and then 2. Then the fluoro is sitting on carbon number 2, basically. What is the substituent? It's 2-fluoroethyl. 2-fluoroethyl. Where is the substituent sitting? Sitting on carbon number 4 on that longest chain of carbons. That's why the name would be 4-2-fluoroethyl heptane. Why do we use parentheses to make sure that we recognize that what's within the parentheses, it's a complex substituent. So we wouldn't be confused between the numbering of the side chain and the numbering of the longest chain. Here's another example. See here that we have longest chain of carbons is 9, so that's nonane. Why do I number from left to right, not right to left? Again, the nearest substituent would be the methyl, and it's sitting on carbon number 2, while bromo is sitting on carbon number 6. If you number it from right to left, you're going to end up having 4 bromo, and you're going to end up having 8 methyl, which you don't want to have that. Your goal should always be the lowest numbering possible for the substituents. Next would be naming the substituents alphabetically. So 6 bromo, 2 methyl, nonane. Here's another structure. We could see basically that's a cyclic alkyl halide. So that will be numbered based on the alphabetical order, since there are 2 substituents. If it's only 1 substituent, I wouldn't need to number it. But if it's 2 substituents, I will number it based on the alphabetical order of those 2 substituents. I have a bromo and a fluoro, so that's why carbon that has the bromo sitting on it would be number 1, and the carbon where the fluoro is sitting would be number 3. So this would be 1 bromo, 3 fluoro, cyclohexane. We recognize that there is stereochemistry here, so I can say cis 1 bromo, 3 fluoro, cyclohexane. The more correct name would be R and S. So R and S. If you do the configuration labeling here, you're going to find that the stereo center here is an R, and the stereo center here would be an S. And then the proper name would be 1R, 3S, 1 bromo, 3 fluorocyclohexane. So the 1R and 3S would be in front of the name in parentheses, followed by the rest of the name here. Because if I leave the word cis, what if I have the bromo down and the fluoro also down? Does that mean that structure is the same exact structure as this one? Of course not. These 2 are actually enantiomers. So that's why it's better to label the stereo center rather than having the word cis or trans. Some common names based on alkyl substituents that we have learned in chapter 3. So this is the isobutyl group. So this would be the isobutyl bromide. This is the 6-butyl. So this would be the 6-butyl bromide. And this is a terbutyl. So this will be the terbutyl bromide. So these are common names. You cannot be using those as IUPAC names. Keep that in mind. So what would the proper name be for this then, or the IUPAC name? You would number the chain 1, 2, 3. So this would be 1 bromo, 2 methyl propane. 1 bromo, 2 methyl propane. What would this one be named? 2 bromo butane. That's if I'm asking you for the IUPAC name. What would this one be? Well, this one would be basically 1 sitting on the center. So this would be 1, 2, 3. So it's 2 bromo, 2 methyl propane. That would be the IUPAC name. Some common names also you're going to probably see in lab. So methylene chloride or methylene halide, that's when you have a CH2X2. Chloroform or haloform for the CHX3. And carbon tetrahalide or carbon tetrachloride would be basically if you have a CX4. So that's also considered to be common names. What would be the IUPAC name? Would be basically tetrachloromethane. Tetrachloromethane, that would be the IUPAC name. Dichloromethane, that would be the IUPAC name. Classification. Just like the very first slide that we looked at, having an alkyl halide versus a vinyl halide versus a phenyl halide, we could also classify them into more categories based on the type of carbon the halide is attached to. What is that supposed to mean? If the halide is attached to a methyl, then it would be a methyl halide. If the halide is attached to a carbon that has another carbon attached to it, that would be a primary alkyl halide. If the halide is attached to a carbon that's attached to 2 other carbons, that means it's a secondary alkyl halide. if the halide is attached to a carbon that has 3 carbons attached to it. So that would be basically a tertiary alkyl halide. Let's look at some examples. Here's the first example where the halide is attached to a methyl. So that's why it's a methyl halide. Here's the second example, or the second category, where the halide is attached to a carbon that has a carbon attached to it. So this is a primary carbon. Therefore, this is a primary halide. Here's another class of alkyl halides. So the carbon where the halide is sitting on, it has 2 other carbons. So that's a secondary carbon. Therefore, this is a secondary halide. And here's the fourth category or fourth class of alkyl halides. That's when you have the halide is attached to a carbon, it has three other carbons. So that's a tertiary carbon. Therefore, this is a tertiary halide. When we get into the nucleophilic substitution reactions, we're going to start using those terms: methyl halide, primary halide, secondary halide, tertiary halide, vinyl halide, phenyl halide. It's very important that we know already what these structures are, and in order for us to understand what's being discussed in those parts in that reaction, the nucleophilic substitution reaction. If you have a dihalide, a structure that has 2 halide groups. Now, those 2 halides, they may be sitting in a certain pattern that will require us to classify that dihalide as the following. So if the 2 halides are sitting on the same exact carbon, that would be a geminal dihalide. Like in this example, what do we have? We have 2 bromos sitting on the same carbon. So that would be a geminal dibromide. If the 2 halides are sitting on 2 carbons that are adjacent, that would be vicinal dihalide. What if they are sitting on 2 carbons that are not adjacent? Then obviously it would be a dihalide, but you cannot use geminal or vicinal. So that's the difference between geminal and vicinal. Geminal, you have the 2 halides sitting on the same carbon. Vicinal, you have the 2 halides sitting on the 2 carbons adjacent to each other. Adjacent to each other. Some uses of alkyl halides, dipole moment. We already know that every single CX will be a polar bond. The polarity will depend on the difference in their electronegativity. The higher the difference, the more polar the bond will be. Due to the fact that the electronegativity of fluoro is more than chloro, more than bromo, more than iodo, we know already that the bond length of CF will be the shortest among the 4. And the bond dipole will be the highest in the CF bond. So that's important to keep in mind. Even though we have polar bonds, doesn't mean the alkyl halides or those haloalkanes have to be polar compounds. It all depends on the geometry of the structure. So here's an example. Yes, every single bond here is polar, but this structure, due to the fact that those dipole moments, they cancel each other out, the overall molecular dipole net is 0. Therefore, it's a non-polar compound. So keep that in mind. That doesn't mean if I have a polar bond in a molecule, that means I should just go ahead and label it polar compound. You have to look at other parts in the molecule as well. Boiling point, you can see here that the longer the chain, the more point of interaction to build up intermolecular forces with molecules of the same, and therefore the higher the boiling point will be. So that's something we actually seen already in the alkane chapter, where we've seen branched alkanes have lower boiling point, lower melting point than the straight chain alkanes. Density wise, usually when you have a mono halide alkane structure, usually is less dense than water. But when you have 2 halides or higher or more, these structures tend to be more dense than water. So here's an example. Methylene chloride, CH2Cl2. It's a common solvent. You're going to see it in lab. It's very common that you're always going to notice that you're always going to find the methylene chloride in the bottom when you are extracting a reaction. Meaning, if you use methylene chloride and water to do extraction, you will find the methylene chloride layer at the bottom while the water layer on the top. Why that is? The density of methylene chloride is higher than density of water. Alkyl bromide and alkyl iodides usually are dense than water due to the atomic size of those halides. Preparation of alkyl halides. We learned in chapter 4 the radical halogenation of alkanes, and we've seen in there that the halide that reacts with the alkane usually tends to find that carbon that's going to be the most stable radical. So if you have basically a propane reacting with Cl2 in presence of light or heat, you would expect the chlorine to be sitting on the carbon number 2. So you will end up making 2-chloropropane. The reason is that the second carbon would be the most stable radical. Therefore, that would be the one that's going to be substituted. So radical halogenation, it's a reaction we learned in chapter 4, and it's very important that you go back and review it if you've forgotten about it, how it works mechanistically, and where the halide will be sitting in those reactions. Bromination usually is more selective. It's an endothermic. Chlorination is less selective. It's an exothermic reaction. There is also the free radical allylic halogenation. What is that supposed to mean? When you have a structure that has basically an allyl group, that you would expect the allylic carbon to be the one that's going to be the most stable radical in that structure, and that will be the one that's going to pick up the halide. And we'll see example in a second. So this is a cyclohexane reacting with Cl2. All of those carbons are secondary carbons, so it doesn't matter which carbon to pick to basically place the Cl on there and getting the hydrogen off with the H, with basically the second chlorine to give you HCl. Here's another example. You can see here that you have a primary and a tertiary carbon. So the tertiary carbon would be the one that's going to be substituted. So you could see here that you end up making basically the terbial bromide. So in all of these reactions, if you have a benzylic carbon, that will be more stable than a allylic carbon, more stable than a tertiary, than a secondary, than a primary. So those allylic halogenation, and especially the allylic bromination, and that's the one that you're going to notice actually being used a lot in this course. The fact that there is an allylic carbon, and what's an allylic carbon? Carbon attached to a vinyl group. This sp3 carbon, it's considered an allylic carbon. And if I have this substrate reacting with bromine in presence of light, that would be expected to go through radical mechanism. So the bromine will be picked up by the most stable carbon as a radical, and that would be the allylic carbon. And you can see here that you end up making 3-bromocyclohexene. 3-bromocyclohexene. So every single time you have an allylic carbon in a structure and you're reacting it with bromination condition, that's radical bromination, you would always expect the allylic carbon to be the one that's going to pick up the bromo. Now, sometime, well, let's look at this mechanism first. So you have basically, in short, you have the bromo radical react with the cyclohexene, pick up basically the hydrogen, and that will be the HBr. The second step would be the radical of the allylic carbon being resonance stabilized. So these two will be basically the two equal in stability as resonance forms for the allylic radical, and that will basically react with the Br2. That will be the second step in the propagation, and you end up basically making the allylic bromide or the 3-bromocyclohexene structure. So this is in short. It's very important that we recognize this mechanism. That's usually the propagation step in the allylic bromination. You are not required to know the initiation, even though you should be able to figure that out. That's the Br2 being homolytically cleaved to 2 Br radicals. And the termination step, where you basically have all the radicals reacting with each other to give you the non-radical structures, and that will basically stop the reaction. In the propagation step, that's where the products are made of a radical reaction. The first would be the HBr, and the second would be the 3-bromocyclohexene. So make sure that you are able to repeat this, please. N-bromosuccinimide. Instead of using Br2 and light to better control the reaction, to better yield the reaction, we tend to use N-bromosuccinimide. So this is only used in allylic bromination structures. So, or allylic bromination reactions. You cannot use it for allylic chlorination. You cannot use it for another type of allylic halogenation. It has to be allylic bromination. The reason why NBS is more preferred than using Br2 for those allylic carbon to be brominated is because it's more selective and it keeps the concentration of Br2 low. So that way you basically brominate one site rather than several sites. So the reaction usually of N-bromosuccinimide will basically react with HBr to generate Br2 in situ within the reaction, and that Br2 will basically find the allylic carbon to eventually brominate it. If I would be using Br2, straight Br2 without using NBS, N-bromosuccinimide, I may end up having the two sites being brominated. I may end up having dibromo carbon instead of a monobromo carbon. So that's where the selectivity becomes important. So N-bromosuccinimide is the method of choice when it comes to allylic bromination. So how do I write that down? Simply, alkene that has an allylic carbon, NBS that basically stands for N-bromosuccinimide. Do I need to write the structure down? No, you do not. Just being able to write the symbol, the short, or drawing the structure is perfectly fine. In presence of light, it's important that we mention this, light, to indicate it's a radical reaction. And that will basically give me two different products. Why that is? Because the radical that's going to be generated on the allylic carbon, which is right here, will be stabilized by a second resonance. Basically, that radical will be on the other carbon. So this double bond will eventually be basically delocalized to be between these two carbons, and the radical being going to be picked up by the tertiary carbon. So now you have a primary allylic and a tertiary allylic. So these two would be expected to be formed in this reaction, and therefore each of these will be reacting with the Br2, and that's why you end up basically making two different products. So one would be the primary allylic, giving you the primary bromo, and the second will be the tertiary allylic to give you the tertiary bromo. So these are important to mention. Every single time you have a radical halogenation and you end up using an allylic carbon in the structure to be halogenated, you always have to consider the resonance form. If it's different, then you're going to end up having a different structure. Like in this case, these two are exactly the same. So that's why whether you brominate this or you brominate that, you end up having the same exact structure. Both of these will end up making 3-bromocyclohexene. But here, the two structures are different. One is a primary allylic and one is a tertiary allylic. So you cannot ignore one of them when it comes to the outcome of the radical halogenation in this reaction. Reactions of alkyl halides. There are two types of reactions that those alkyl halides will undergo. One will be discussed in chapter 6, that's the nucleophilic substitution, and one will be discussed in chapter 7, that's the elimination. Nucleophilic substitution is basically when you have an alkyl halide reacting with a nucleophile, and we'll see examples of those nucleophiles, and the nucleophile will end up substituting the halide. So you end up making a structure out of this nucleophilic substitution reaction where the halide is kicked off and the nucleophile will be substituting that halide. So you end up making basically this structure. And we will learn the two types of nucleophilic substitution that are SN1 and SN2. Elimination is basically it's a reaction in which you will have a strong base, and this base gonna deprotonate the hydrogen on the alpha carbon. So here's your CX, and here's the alpha carbon. Once it deprotonates that hydrogen, that bond, CH bond, will go back and make the alkene, and that will kick off the X. So you end up basically doing three things at the same time. Base, picking up the hydrogen, the CH bond will go back and make a double bond, and the third thing is going to happen, the CX bond will be broken apart to give you X minus. So basically you end up making an alkene compound out of those elimination of alkyl halides. And once again, this will be covered in chapter 7. And Next, we will be talking about those two types of nucleophilic substitution, SN1 and SN2.